You know, when you see one of those incredible videos of a humanoid robot, have you ever stopped and just wondered what is actually going on inside its head? How does a bunch of metal and wires learn to walk, to see, to actually interact with the world around it? Well, today we're pulling back the curtain. We're going to look at the actual blueprint for building the intelligence inside a modern robot.
This is the big question, right? And it's not science fiction anymore. This is one of the most fascinating and frankly difficult engineering challenges of our time. So in this explainer, we're going to walk through the essential components step by step to figure out exactly how it's done.
To really get our heads around this, we need to think a little less like programmers and a little more like, well, like biologists. We're going to build the anatomy of a robotic mind, piece by piece, right from the ground up.
Okay, so it all starts with this one core concept: physical AI. Now, this isn't just about some smart software running on a server somewhere. Physical AI is what lets a machine actually perceive the real world, reason about what it's seeing, and then physically interact with it. It's the critical point where the digital brain meets the physical body. So, where do you even start? Well, just like any animal, before a robot can think or move or do anything really, all of its parts need a way to talk to each other. It needs a nervous system. And that brings us to our first major building block, ROS2. It stands for Robot Operating System 2. The best way to think about this is as the robot's central nervous system. It is the absolute communication backbone that connects everything, the motors, the cameras, the balance sensors, all of it, into one single functioning system. This nervous system really has three key jobs. First, the architecture lays down the foundational structure for everything else. Second, the communication layer manages all the data flowing back and forth. And finally, the robot models create a virtual definition of the robot's body, what it's made of, and all the ways it can move.
Okay, so we've got a nervous system. Awesome. But you can't just flip a switch and hope for the best, right? Learning in the real world is messy, it's slow, and it's risky. What if the robot breaks something, or itself? It needs a safe place to practice. And the solution to that problem is the digital twin. It is a perfect one-to-one virtual replica of the robot and its environment. Think of it like a super realistic video game. In this digital sandbox, our AI can try to walk, fall down, and learn from its mistakes thousands, even millions of times without any real-world danger. It's learning at hyperspeed in a totally safe world. Now, to build this virtual playground, engineers use some really powerful tools. On one hand, you have something like Gazebo, which is a total workhorse for setting up the physics and plugging in all the simulated sensors. And on the other hand, you can use a game engine like Unity to bring incredible photorealistic detail to the simulation. The crazy part is, both of these can talk seamlessly with that ROS2 nervous system, letting the robot learn in a world that feels incredibly real. All right, let's recap. Our robot has a nervous system and it has a hyper-realistic digital gym to train in. But something's missing. The athlete, right? What's actually doing the learning? This brings us to the most critical step of all, giving our robot an advanced AI-powered brain. And this is where things get really, really interesting. We're moving beyond just basic commands and into true perception. The robot isn't just following a list of instructions anymore, it's actually starting to see, to map, and to understand its surroundings. A huge player here is NVIDIA's Isaac platform. It provides the specialized tools to make this all happen fast. For example, there's a technology called VSLAM. This lets the robot build a map of a room while at the same time tracking its own location inside that map. I mean, that's a complete game changer. A robot that doesn't know where it is just a lost robot. And all of this is powered by GPU-accelerated models that give it the raw horsepower to perceive the world in real time. So we have a nervous system, a digital practice ground, and an AI brain that can perceive the world. Now for the fun part. Let's connect all of this together to create intelligent, useful action. This final piece of the puzzle is a paradigm called Vision Language Action, or VLA. This is the framework that brings it all together. It's the bridge that connects what the robot sees and hears with high-level thinking. It's what turns a simple command, like, hey, get me a drink, into a series of complex physical actions. And the workflow is actually pretty elegant. First, the robot perceives the world through all its cameras and sensors. Second, it understands a command, say, bring me the blue cup, using things like speech recognition and large language models to figure out a plan. And finally, it executes that plan, translating that digital strategy into precise physical movements. Perceive,
understand, execute. It's that simple.
And there you have it. When you put these four modules together, the ROS2 nervous system, the digital twin for practice, the NVIDIA Isaac brain for perception, and the VALA framework for action, you have the modern blueprint for a thinking machine. This is how physical AI is actually being built today.
And this brings us to one last really big thought. We have the foundational blueprint now. We know how to create intelligent machines that can see, understand, and operate in our world. So the question is no longer just how we can do it. The real question is, what kind of future are we going to choose to build with it?